Okay. Yeah. Hi, everyone. I'm Jinjin, and I'm here to present our work on a vision system for discovering physical errors in video analytics systems. This is joint work with Ted and Sanjay here, as well as Stavros and from University of Chicago. So let's begin. When we think about visual video model deployment, once we finish training the model and we want to send it out into the real world, where there's various scenarios where we can implement this model, and these can get very complicated and very diverse. For example, we have like for just an object recognition model, we might be interested in tracking people in homes. We might be interested using the same or a similar model for tracking pedestrians on a AV system, or we might be interested in surveillance, tracking people and cars and bikes in public spaces. Each of these deployments and deployments within these types of systems introduce a new complex environment in which we might have not seen during training and in which our model has to interact with. So and just interactions, we've seen through our preliminary experiments that interactions with these environments seem to correlate with errors that occur in the model. For example, some training data on the Virat data set, we can see that given an average scene of a sidewalk, we have overcounting and undercounting of pedestrians that correlate with like visual features of that scene, such as the lamppost, and then undercounting at like places further away and places obstructed by trees and other visual indicators. So it seems like as a human looking at this picture, we can have some intuition about the interaction between the model and the scene, but it doesn't seem like existing video tools give us a good systematic capture of that kind of intuition. For example, if we're looking at what things that low level pixel level explanations give us, that tells us like where in the image or like what groups of pixels contribute negatively and positively to the explanation, but it doesn't tell us like what feature about that scene in particular is leading to that contribution by that group. Again, when we're thinking of low dimensional solutions, so if we're trying to think of if there exists existing work extending those pixel level explanations and trying to think about like more table form features such as luminosity and like obstruction, and seeing how those correlate to video errors. And we would think that these are more closer to our problem of considering physical examples, but this isn't explicitly highlighted in these features, and how we formulate those physical errors is not well explained in these previous works. For example, for a random forest, it doesn't, which is an explainable model tool where you can explicitly look into how the model is classifying these features. It doesn't tell us like the exact if those features are what we're finding useful. And then a lot of the categorization of those features are also obtuse and not directly correlated with our intuition of the physical world. So then what is this intuition that we're trying to capture? When we're thinking about physical errors in our experience, that these have like specific causes, such as lighting, obstruction, distance from the camera, if some object is too small, or lookalikes in the system, if there's something that kind of looks like a dog but is actually a fire hose, that might be misclassified as a dog. And this categorization is some different from what these previous systems offer, because what we can realistically capture is not actually these like complex concepts that exist in the physical world, but like these proxy indicator data streams, such as intrinsic time streams about the video features, such as luminosity, the edges in particular in areas of the video, the dominant color in the video, as well as extrinsic features as network and audio of the video. And so our question is, how can we link these things that we realistically capture and that like previous video systems have tried to do analysis on, and those like actual real world physical causes of like errors? And an example of why this is important is because like no matter what, our time series is not perfectly representing the physical world. For example, we would think that luminosity of a bounding box would do a pretty good job of capturing how dark that scene is. But if we actually make a histogram of a data set for specifically analyzing the luminosity feature, we will see that a lot of times the bounding box is correctly analyzing features with very low luminosity. And the reason, if we dig a little deeper, is that we are seeing silhouettes of like people who are very dark or who are in the shade, but with clear silhouettes. So there is, going back to this slide of like data streams and errors, we can clearly see that there is a middle missing link of causes. And so how to address that is what we want to focus on in today's presentation. And we're presenting a vision for a human in the loop error detection system that allows us to capture some of these physical causes. And we want to take in data streams such or time series of like extrinsic and intrinsic features, as like we proposed before, as well as training videos and model outputs. And we want to use these auxiliary indicators to be able to and calculate environmental errors and to understand them. So after taking in this data, we're proposing a system loop of have automatic data analysis as well as selective human labeling, and integrating both of them in order to capture these causal environmental features. Firstly, for the automatic data stream analysis, we propose this idea taken from statistics of discontinuity analysis, where we are analyzing changes in the time series where errors occur. And this is possible because we have the explicit training data of true and model labels. And we can directly see, as shown in the graph above, when the features change in correlation to time stamps where accuracy also drops. And the reason that we want to do this kind of analysis instead of just looking for explicit correlations is because of what we see here, where it's not obvious based just on by distribution or based or globally whether a feature is actually correlated with an error, but we can specifically pinpoint those that like more indications of causation by looking at like specific changes. And but of course, as we've talked about throughout today, that and really in order to do causation, you need to bring humans into your problem, and you need to have some human verification that those features and those like time streams actually correspond to the causal errors. And based on what we gather from the automatic data stream analysis, we want to be able to pinpoint specific scenes and select samples in order to ask the humans if what we think is happening in that scene is happening, and to verify what kind of thing is happening, because we don't quite know that from automatic analysis. And so after in our vision system, after doing some data stream analysis, we're presenting questions such as what type of error is happening in the scenes, and we want to present categorical answers that are easily understood and help us selectively label the data. And we are aiming to apply some kind of weak supervision system to feed those labels back into our time analysis to verify our final answers. And then again, after finishing this loop, which is on the training data, that is like when our initial example of deployment comes in, and now we can take these facts and these indicators learned from the training data into new video deployment systems. And the nice thing about what we want to propose is that this allows us to basically air analyze physical environments without actually having to see those environments, because we can find auxiliary features that correlate or in an interesting way with causes, and automatically detect when those causes may occur without having to have a visual image of that scene sent to the original data scientist. And I think this will be good for deployment because it resolves some issues such as like privacy. And yeah, I guess that overall that's the general system that we're proposing, and that's the general problem that we are seeing that still needs to be addressed in video deployment. Thank you everyone for staying so late and for this final talk. And
Dominic, I really like this this overall idea here of not just building a system that helps people understand or like make predictions about data, but also about like the potential, I guess you could call them blind spots of a model, and building a model, I guess, to explain what the issues are. So you're specifically looking here at video conference or video analysis. I think I've seen similar work in other domains. What have you borrowed from other domains where similar techniques were used? and how might this maybe apply to those domains as well?
Yeah, for sure. That's something that we've talked about in discussions. We really focus on video because of two factors that we've talked about, which is that like in humans have some intuition about the physical world, and we can interact with the physical world in some way. For example, if there is an object like in the scene, maybe we can change the video angle, and or maybe we can remove that object. And those are very actionable things that have a lot of intuition in video, as well as the fact that we can take advantage of the fact that like time is continuous, and we can consider analysis of time series. I think that we definitely we're definitely are borrowing ideas from other fields that I guess haven't been explored as deeply in video. Like for weak provision, we were looking at things like the snorkel paper, and for like discontinuity analysis, I've also already mentioned that that's something that's been applied very often in statistics. So I think there is definitely that interlink there.
Thanks for the talk. I'm struck when you talked about the different kinds of causation, the reasons that the model might be going wrong. The causes are all pretty standard regardless of application. Meaning it could be a self-driving car or a pedestrian detector, or an emergency or fire detector, and yet the explanations are generally optical or other qualities of the actual video feed. Have you ever considered integrating domain-specific explanations? Like, the reason I couldn't detect this is the ambulance arrived too early, or the car went by too fast, and I'm trying to do car detection, or the pedestrian was wearing a funny hat, something like that. It seems like there's a lot of these explanations that probably exist tied to the application you're actually trying to focus on.
Yeah, I think that makes a lot of sense. And I think that's definitely something that we want to do in our final system. One of the reasons we haven't discussed those causes was that like these are more generally applicable, I think, and immediately understandable to the audience. But I think really this type of system should be able to work for both model specific and like general environmental causes.
Okay, great.
Yeah.
Thank you. Were there other questions? Oh, go for it, Tom.
Yeah, and maybe following up to this question, could you automatically mine classes of potential errors? So let's say you have a video feed, there's certain errors happening because you have ground truth data. Now you have thousands of errors. Can you classify them maybe into like, okay, here's one cluster of issues, and then a human could look at it and say, well, that's issues with lighting. Here's another cluster of issues. So rather than looking at, I think you did labeling of individual examples, maybe do it of even a larger class of errors.
I think that's one thing we want to aim for, but that's actually a very, very hard problem, because that's when we try to run some like global analysis of those features, for example, like running a random forest, we found that these features there's too many other spurious correlations that seem stronger to like at a global level, and or that like there are just too many like other correlations with things like scene specific features. So I think eventually, in order to actually have deployment explanations, we need to have some global explanation, but to start off and to immediately generate those global explanations is very difficult.
Oh, thank you. No other questions then?